We will learn QPSK Demodulator. Actually, we went through the theory in my last class, and today we are going to learn the simulation model. So we will see how to simulate this QPSK demodulator. QPSK demodulator. Just to recall that we should have the received signal R of t, which is actually a QPSK modulated symbol, because we are observing this demodulator in the absence of channel effects and noise. So ideal demodulator will be observed in today's simulation. Now what we will do with that R of t, we will multiply our cosine carrier here, and this product will go to the integrator, and at the output of the integrator we have some R1k, some we will see that this would be some value, some number. And then we have a threshold detector. We will see that this threshold detector is implemented with the help of signum function, which will give us a 1 or a minus 1. For all positive value it will output a 1, for all negative value the output will be minus 1 from here. So this way we get our data from the upper branch, one bit from the upper branch and one bit from the lower branch. Now keep in mind, we will see our simulation model for one time interval, so from 0 to t. So let me recall our modulation, the QPSK modulator, because we need that signal which we generated in the last video. So I'll go to my file, the QPSK modulated signal. Let me see the QPSK modulated signal, which we actually we run this code in the previous video, and we saw that we can generate our QPSK modulated signal in the end. Let me run it step by step, and let me recall that simulation model first. We actually generated our data was this one 1 0 1 1 0 0 0 1 1 1, right? So we generated this I of t, cos of 2 pi f c t first, and it is given in this code here. So let me run the code till that point. I'll put a breakpoint. So let me put a breakpoint over here before this plotting command, because here from or let me run it once. Let me put a breakpoint here, so that we get I of t cos of 2 pi f c t, I of t cos of 2 pi f c t from our signal. Okay, add this to path, and I just put a breakpoint here, and I'll run this command, and another breakpoint I'll put it here, right? So that this we see the signal. So this is actually this code which we run in the previous slide gives you the signal, this signal I of t cos of 2 pi f c t, which is just we separate, just recall yourself that we separate odd number of ones from our data, and for odd number of bits, and for odd number of bits we generate I of t like 1 1 0 0 and 1. So it's minus 1 representation I of t, NRZ signal, and we multiply cos of 2 pi f c t with our NRZ signal to get modulated cosine carrier, right? So in the plot it is up to here. So we have this cos of t and a modulated carrier. The line number 8 gives you the code for this product. So let me run it. I'll run this file, and this we saw that we can generate our NRZ signal. See, this is positive level, negative, and a positive level. This is our sinusoid for 5 time intervals. We have taken this signal for 5 time intervals. So t is equal to 1, capital T, the time period for a signal is equal to 1, and we have taken 200 samples as I discussed in my previous lecture. Now this is our final I of t cos of 2 pi fct, which is shown here finally, the product of the first waveform with the second waveform. Now if we run it further, let me run it, step out, and this is the second q of t sine of 2 pi fct, because if you recall, we had the q of t in this form representation. These were for the even number of bits, and we generated this waveform q of t sine of 2 pi fct, which was this signal, and it is given in our it is given here in this figure. So we generated this waveform for q of t sine of 2 pi fct, and then a QPSK modulated signal, which is this one, s of t, the summation of these two waveforms. Actually, we should have negative sign here because our side 2 of t is negative. And we generated this one. Let me run it till to the end, and we had our signal, modulated signal waveform, which is this one. So you can see our signal, it's very similar to the one which is given in this our figure number 3. So let me show you figure number 3. So our figure number 3, and I'll put it in front of this code. So my figure 3. So this is what we generated, a QPSK modulated signal. Now we have to observe the operation of a demodulator, and we will take this just this first signal from 0 to 1, this one, and we will try to demod, because this symbol actually, the first symbol, which is this one, represent a 1 and a 0, right? So our data is 1 0 double 1 and so on. So this is actually, this is a representation, this symbol represent the binary data 1 0. Now we would expect that our demodulator, which is shown in this figure, here we should get 1 and here we should get 0, right? We should, or minus 1, which is the representation of a 0. So 1 and 0, we expect that our modulator, ideal demodulator, after going through this process, should give us 1 here at the output of this threshold and a minus 1 here, right? And this is what this would be seen right now. So let me take only the first first symbol, and I would say my first symbol is just from a time interval, the first 200 samples, right? The first 200 samples of my signal, because these we have taken 200 samples in this 0 to 1. So the first 200 samples of my signal, which is here, the variable used for this one is this is QPSK ST. This is my QPSK S of t, QPSK modulated signal, which is the sum of the two sine and cosine carriers. So I'll take just first 200 samples, and then we would like to demodulate this signal of the first period. So let me take the first 200 samples, and I will call it, this is my symbol, just first symbol, which is QPSK. This is actually R of t, QPSK symbol, QPSK S of t, but I'll just take the first 200 samples, right? I'll take the first 200 samples from this one. And similarly, I'll take the time interval only up to the time interval would be just the first 200 samples of t, which is 1 to 200. So this is my time interval. Let me plot it and see whether we actually got this first symbol or not. So let me close all first, because I don't need now the other plots. and I'll plot my first symbol. So this is my first symbol, which we have to which represent the data 1 0, and we need our demodulator to decode it as 1 0. So let's see what our demodulator actually is should represent. Now if you see our r of t in the first symbol, we have received signal, we generated this one. This will be multiplied with this under root 2 over t is 1, right? Capital T is 1, so under root 2 times cos of 2 pi f c t. So uh, let me generate this product first. So I'll generate this product, and I'll say the product is equal to my signal, symbol 1, which is the received symbol, multiplied by the carrier, which is I would write it in bracket square root of 2 multiplied by cos of 2 pi fc, and the time interval is just first time interval. So this is the product. Well, there is a syntax error, so I guess I did not, I should have one more bracket. Okay, the function is also is a mistake here, is a cosine, cosine, cos of this one, right? So we just generated our product, the signal. Let's see how it looks like. So let me plot it. Let me plot this signal. Let me plot this signal. Plot the signal versus. Let me see how this product look like. So it's this is from 0 to 1, and this is our product. You can see, just I'll magnify it a little bit. You can see your signal, which is actually the product, and you can see that it is if because this product has to be integrated, and we can observe that it's a very small area, negative area, so mostly it's positive, so that after the integration we would get a some number which is positive, some value which is positive, right? So let me close it. So this product, as shown in this diagram, the product here, I showed you the signal in the upper branch, which is at here. This product should go through this integrator, and it will give us this r1 of k. So if I show this product, uh, actually I have to integrate it. So let me integrate. The integral actually is implemented by the summation, because we have just 200 discrete samples in 0 to 1, in the time interval 0 to 1, and we would like to integrate it. So right, let me give it a name. This is the output of my integrator, and my integrator is the output of integrator, which is just a value, but we expect that this should be some positive value, because it goes to the threshold detector. And if you see the threshold detector, let's see what actually our integrator is. So it's some positive value, right? Now we have the threshold detector function, and the threshold detector function is a signum function. This is implemented as a signum function. For any positive value, the output will be 1. For any negative value, the output will be 0. So I'll implement this one using the signum function. The signum of the output of this is the output of the integrator. So the signum of this is 1. So at the output we got 1, right? So this is how we integrate. This is how we integrate our upper branch. So if we see here, we got a 1 here. Now we would expect a -1 here, because our first symbol was carrying 1 0. It was carrying 1 0 bits. Now in the second branch, we already got this 1. Now in the second branch we have to multiply it with minus under root 2 over t sine of 2 pi f c t. T we have taken 1, so minus 2. Let me find that product. So now is for the second branch. Let me clear it, right? We go to the second branch. In the second branch, let me give it a name, product 1. And product 1 is minus the signal, which is symbol 1, should be multiplied with our carrier, which is minus square root of 2 times sine of 2 pi f c t. 2 pi f c, and our t is just one symbol. So this is the second product, and let's see how the output of this how the output looks like. So this is my product 1, and you can see when we multiply it with the sine carrier, the same r of t give us this signal, and you can see it's a very small area. This is 0, right? So a very small area. If we integrated, a small area is positive, mostly the area is negative, so overall we will get a number which would be negative. So we integrate. Now I showed you the signal over here, this product. This would be integrated for the first time interval. So let's see what's the output of the integrator. I'll give it a name, integral 1, and this is the summation of the prod 1. So this should, we expect that this should be negative, right? So it's actually a negative number. Now this negative value or this negative number goes to the signum function, and when we apply the signum function over here, the threshold detector actually, which we apply as signum function in the in the octave. So if we go to the signum function gave us minus 1, right? So here we get a 1, and from this branch we get a minus 1, and this is the parallel to serial converter. We got two parallel bits, 1 and a minus 1, and it will be 1 and minus 1, and this is what we actually transmitted from the modulator. This is what we transmitted from the modulator. So for the first symbol we saw the operation of a demodulator, and actually we got our signals. So keep in mind, we just used to summarize it, we showed the demodulator, the process of the demodulation just for the first time period 0 to t. So we saw that our signal is for the first we just processed our received signal for the first time interval. We passed it through the upper branch, multiplying it with the psi1 of t cosine carrier, and we saw that we got the integrator gave us a positive number that was applied to the threshold detector. In the simulation we used the signum function, and it gave us a 1 for positive value. Similarly, for a negative, this was the received signal was multiplied with minus 2 under root 2 over t sine of 2 pi f c t, which is psi 2 of t. We integrated this product. The integral gave us a negative number. When we applied it to the threshold detector, we got minus 1. This way a 1 and a minus 1 was received. So this is all about our threshold detector, and you can just I just showed this for the first symbol. You can try other symbols. You should be able to receive the corresponding data which is represented by those symbols. So try this one for S2, S3, S4 and